It is the invisible lifeblood of modern industry. It drives the massive turbines that light up our cities. It provides the heat necessary to refine crude oil into gasoline and turn wood pulp into paper. It is steam. But we aren't talking about the steam rising from your morning kettle. We are talking about high-pressure industrial steam, a force so potent that if mishandled, it carries the explosive potential of a bomb. When we enter heavy industry, we are talking about pressure starting around 1,000 psi and climbing to over 3,200 psi. Thermodynamics tells us that as you increase the pressure on water, its boiling point rises. At 1,000 psi, water doesn't boil at 100 degrees. It boils at nearly 285 degrees. This means the steam carries vastly more thermal energy. In the early days of steam, think locomotives and the Titanic, boilers were generally fire tube designs. Fire goes inside the tubes. Water surrounds them in a big tank. This works great for low pressure. But if you try to pressurize that big tank to 1,000 psi, the metal walls would have to be impossibly thick to stop it from blowing apart. To reach high pressures, engineers had to invert the design. They created the water tube boiler. It is much easier to contain high pressure inside a small diameter tube than in a large diameter drum. This is due to hoop stress. Almost every high-pressure industrial boiler today is a water tube design. Some are tall enough to fit the Statue of Liberty inside. Let's identify the major organs of this beast before we turn it on. We'll start with the heart. First, the heart, the furnace or combustion chamber. This is where we burn fuel, coal, gas, or biomass. Next, the brain, the steam drum. Located at the very top, this vessel is where the magic happens, separating steam from water. At the bottom, we have the mud drum. It's the kidney of the boiler, collecting sediment and impurities to be flushed away. Connecting these drums is the circulatory system. We have downcomers outside the furnace and risers forming the furnace walls. Let's fire this thing up. Rule number 1, you do not just hook a garden hose up to the inlet. The water must be unbelievably pure. Any minerals or oxygen will scale up the hot tubes. If the water can't touch the metal to cool it, the metal melts. Boiler explosion. The feed water enters the economizer. A boiler is a heat vampire. It wants every last BTU out of the fuel. The economizer uses exhaust gases to preheat cold feed water almost to its boiling point. It's free energy. The water now enters the steam drum, but it doesn't stay there. Cooler, denser water sinks down the external downcomers. Now, it enters the risers exposed to the terrifying heat of the furnace. As it absorbs heat, it begins to boil. This is called natural circulation. Heavy water in downcomers pushes down, forcing the lighter steam water mixture in risers up. No pumps are needed, just thermal physics creating a violent loop from the bottom drum to the top. The mixture arriving back at the steam drum is chaos, but the turbine needs pure, dry gas. Water droplets act like bullets. First, centrifugal cyclones spin the mixture. Heavy water is flung out, lighter steam rises up the center. Then, rising steam passes through chevron dryers, mist droplets slam into metal plates and drip down, dry gas exits. We have dry, saturated steam, but if it loses even 1 degree, it turns back to liquid. We need a safety buffer, superheat. We route that steam into the superheater. Here, its temperature rises far above boiling while pressure stays same. At 2,000 psi, we crank the temperature up to 540 degrees. This steam is incredibly energetic and ready to power the turbine. Running one of these is a constant balancing act managed by sophisticated distributed control systems. Risk 1, low water level. If the drum runs dry, circulation stops, riser tubes overheat and rupture instantly. Catastrophic. Risk 2, overpressure. Every boiler has redundant safety valves to vent lethal energy instantly if the turbine trips. These machines are marvels. They take raw chemical energy and discipline it into the fluid that powers our world. Next time you flip a light switch, remember the massive, silent cathedrals of pipes and fire that made it possible. Hit that subscribe button and the bell so you don't miss our next teardown. This is Simple Guyane, signing off.